UMAT stands for user material, and by using it you have the ability to define any complex material models that cannot be defined with the models available in Abaqus. And UMAT does the same thing but for explicit solver. There are many subroutines in Abaqus to define the model of the material properties and behavior in different situations. For example, by UHARD and VUHARD you can define a user-defined material behavior that includes hardening for plasticity. Or by using USDFLD and VUSDFLD you can define field variables at a material point as a function of time or any available quantities. For example, you can make a property of your material such as the damage criteria dependent on one of these field variables. UHyper used to define hyperelastic material behavior, and many other subroutines that make it possible to simulate the latest material model easily. But UMAT is the most famous subroutine for defining material behaviors. This is because UMAT and VUMAT have a very high ability to define various behaviors such as different types of elasticity, plasticity, damages, and many other properties. Well, now let's get to know UMAT more. We define the material using the UMAT and VUMAT. What does that mean? What we are doing in these subroutines is to redefine the relation between stress and strain for Abaqus, but in a way other than the methods of Abaqus material library. When it's come to the relation between stress and strain, the first thing that comes to mind is Hooke's law. A linear relation, that is Hooke's law, connects the stresses and strains of the material inside a continuous elastic material such as block of metal or a steel bar. As you know, this linear relation is expressed by a factor called Young modulus. But what if the assumptions of being isotropic or elastic or other assumptions are not true for a material? Here is where we need to define this relation due to the behavior of the material. Later we return to Hooke's law and the relation between stress and strain. But before that, let's take a look at the subroutine's structure. What exactly does a subroutine do? First, in Abaqus standard, the user-defined material model is implemented in the user subroutine UMAT. And in Abaqus explicit, model is implemented in VUMAT. This means that you can use UMAT when you use a step that Abaqus standard solve it, such as static or dynamic implicit steps. And you can use VUMAT for steps that solved by Abaqus explicit solver, such as explicit dynamics. You can use these subroutines when none of the existing material models included in Abaqus material library accurately represent the behavior of the material to be modeled. These interfaces make it possible to define any proprietary constitutive model of arbitrary complexity. User-defined material models can be used with any Abaqus structure element type. Multiple user material can be implemented in a single UMAT or VUMAT subroutine and can be used together. In this tutorial, the implementation of material models in UMAT or VUMAT will be discussed and illustrated with a number of examples. Proper testing of advanced constitutive model to simulate experimental results often requires complex finite limit models like advanced structural elements, complex loading conditions, thermomechanical loading, contact and friction condition, or complexities like these. With these subroutines, you can define any complex model with any elastic, plastic, damage, or any other properties. It can be defined for any element in Abaqus. You can also define multiple materials at one subroutine. As a user, you should concern only with the development of the material model. But it's not bad to know about the structure of Abaqus and where subroutines are used in the simulation process. Consider this figure as a decision point and this shape as an action point. The first thing we need to do in an analysis is to define the properties of the problem, including geometry, material, method of solution, and so on. Then Abaqus enters our defined step solution. To do this, the step time is divided into smaller parts called increment. As you know, the Abaqus standard is a solver in which the solution process is done as an increment by increment to the end of the step, and according to this, the essence of the solution process is based on calculating stress and strain in the increment by increment form. Unlike the explicit solver and its different method, which we will talk about later. In fact, in the implicit method, the standard solver, the stress at each increment is calculated from the stress on the previous increment. As you know, in the case of an implicit solver, we seek the equilibrium after at every increment by checking the difference between externally applied force and internal reaction force. This difference is called residual. Abaqus uses a tolerance value close to 0 defined in its solver setting. Till the difference between the forces comes under this tolerance value, the solver carries several iterations. Therefore, Abaqus carries out iterations within an increment in order to attain equilibrium. After the starting of iterations, a stiffness matrix K is created, and after the loads are defined. Then the differential equation is solved. Each subroutine in each of these steps defines a part of the simulation that cannot be defined with the tools available in Abaqus. For example, imagine that a load has a complex function or is dependent on variables that cannot be easily defined in Abaqus graphical user interface. Defining load by dload instead of the load module is the solution. Abaqus will call the subroutine to define the load in this step. Also, you can see other subroutines and when they were called by Abaqus in the simulation process. Of course, the definition of this section is not related to our tutorial, and for more explanations, you can see the Abaqus subroutines overview package if you are interested. This is the part we're dealing with, where UMAT is called and the stiffness matrix is formed. If the equation does not converge, it goes back to the beginning of the iteration and repeats it with new values. If it is convergent, the results are recorded and the next increment begins and the solution continues until the step is complete. If there is another step after that step, solving that step will start. Otherwise, the simulation is completed. Well, let's take a closer look at the main part. I mean calculation of the stiffness matrix. As mentioned, after the starting of an iteration, the stiffness matrix is calculated. If we want to be more precise, after calculate integration point field variable, first delta epsilon is calculated, then consistent Jacobian and stress is calculated. Finally, loads are defined by calculating the partial derivatives of P with respect to X. This flowchart actually is idealized. In the first iteration of an increment, all of the user subroutines shown in the figure are called twice. One time during the first call, the initial stiffness matrix is being formed using the configuration of the model at the start of the increment. And second time during the second call, a new stiffness based on the update configuration of the model is created. And in subsequent iterations, the subroutines are called only once. In these subsequent iterations, the corrections to the model's configuration are calculated using the stiffness from the end of the previous iteration. Many widely used subroutines edit the variables in this part of the simulation for the Abaqus. Here are some of them. Most of the subroutines related to the definition of the material are located in the Jacobian determination block and the stress calculation, like UMAT. So our goal in solving the implicit finite element is to calculate the consistent Jacobians, which we call it C, where delta sigma is the increment in Cauchy stress and delta epsilon is the increment in strain. The parameters mentioned in the previous slide, C and sigma, are the two main parameters that must be specified in the UMAT subroutine. The stress tensor is called by stress intense, which indicates a stress tensor at the beginning of the increment, and also we should update it to the stress tensor at the end of the increment. And C in UMAT called by DDS-DDE, which indicates the Jacobian matrix of the constitutive model. To define these variables, you must copy the subroutine interface to a coding editor software and edit it. I'm using the Abaqus 6.14 and I'm editing the subroutine with Visual Studio 2012 and the 2013 Fortran for compiler. The interface of all subroutines is in this section. First, I choose the standard solver and then the subroutine. Here is a detailed description of the UMAT and its mathematical features and equations that will help you. Of course, most of these explanations are included in this tutorial and subsequent tutorials. This part is the subroutine interface for UMAT. As you can see, it has three sections. In the first part, the input and output variables are defined. The DDS-DDE and stress variables we'll talk about are here. I will review and explain other variables as well. In the second part, the matrix dimensions of each of these variables are determined. This part, which is written in italic, is the part where we have to delete and write our code instead.
This is a small part of the UMAT and VUMAT subroutine for Abaqus training package. There is a lot more valuable information in other parts of this package that you can get on our website. We suggest you do your project by saving your time and getting basic training so that you don't get tired of Abaqus errors.
Well, I need to explain these variables to you now, but I rather talk about the theory of the problem beforehand. This will help me explain the parameters and the equations and matrices. Seeing this section depends on you. Follow if you are interested. Well, if we go back to a few previous slides, we said that to determine the relation between stress and strain, Hooke's law is one of the most usable models. According to the law, stress and strain for elastic materials have a linear relation, and the Young modulus coefficient determines this relation. Consider a rod of elastic material that's subjected to axial load. Its tensile stress is linearly proportional to its fractional extension or strain by the modulus of elasticity. This relation is a simplified type of stress and strain in one direction and in the form of a scalar. But stress and strain are generally not scalar quantities and are tensor. The object or an element of it can be subjected to normal and shear stresses on each of its planes. So, we define Hooke's law in a matrix form, and in index notation we have this equation. In a Cartesian coordinate system, the stress and strain tensors can be represented by 3 in 3 matrices. For example, the stress can be represented by this. It is often useful to express the anisotropic form of Hooke's law in matrix notation, also called Voigt's notation. To do this, we take advantage of the symmetry of the stress and strain tensors and express them as 6-dimensional vectors in an orthonormal coordinate system as this. So the stress and strain vectors expressed as these, where gamma ij is the engineering shear strain and equal to 2 times of epsilon ij. This engineering shear stress is one of the difference between writing UMAT and VUMAT subroutines, which we'll cover later. With the help of vector form of stress and strain, Hooke's law can be written in a matrix form like this, where D is the stiffness matrix and it is sometimes indicated by the letter C. As you can see, this matrix has 36 components. Due to the inherent symmetry of the stiffness matrix, only 21 elastic coefficients of the latter are independent. This number can be further reduced by the symmetry of the material. If the material has a symmetrical plane, the matrix has 13 independent components, and it's called monoclinic material. 9 for an orthotropic material with 2 symmetry plane like composite material. 5 for transfer isotropic material, which is symmetric about an axis that is normal to the plane of isotropy. Finally, an isotropic material is a uniform in all orientations that has 2 constants. In this tutorial, we will look at some examples of isotropic and orthotropic materials. To do this, we examine the stiffness matrix and Jacobian for the isotropic material. Well, let's take a look at generalized Hooke's law for multiaxial loading. So let's start with the uniaxial load again. So we have an uniaxial load in just one direction. We know that Hooke's law is that stress equal to the Young modulus times strain. And so if we have a part and we apply a load in this direction, then the piece will elongate, and so we end up with an axial strain, and it also has some deformation in the other direction, and we call this the transfer strain. And this transfer strain related to the axial strain through the Poisson's ratio. So this is the uniaxial law. So in order to find strain in multiaxial loading, we should apply the principle of superposition. We have epsilon in direction 1 equal to sigma 1 divided by E, and also epsilon in direction 2 equal to negative Poisson's ratio times strain 1, which we can replace with this, and epsilon 3 is the same as strain 2. Let's change epsilon 1 to epsilon 1 1 so that we can use it in the matrix by writing in notation in full. We also have epsilon 2 2 and epsilon 3 3 and sigma 1 1. We also have a similar relation for sigma 2. And Hooke's law for shear stress and strain is as follows. So, similar relations are obtained for shear strains. Now, if we have all these stress at the same time, the following relation are obtained for strains according to the principle of superposition. All I have to do is rewrite these equations in a matrix form with stress and strain vectors and stiffness matrix tensors. This is called generalized Hooke's law in matrix form, where gamma ij is the engineering shear strain. Well, to calculate the stress, we have to get the inverse of this relation. The inverse relation may be written as this, which can be simplified thanks to the Lemma constants like this. In vector notation, this becomes like this, where I is the identified tensor, sigma ij is the stress tensor, epsilon ij is the strain tensor, and gamma is Lemma's parameter, and mu is the shear modulus. The shear modulus is sometimes indicated by G, and Lemma coefficient and shear modulus can be defined as follows. Also, Hooke's law may be written in terms of tensor components using index notations as this, where delta ij is the Kronecker delta. So, this is the equation you need for UMAT, and you also need these equations. So the first one is isothermal elasticity equation with Lemma's constants. The second one is a German rotational rate form, and also we have German rate equation which is integrated in a rotational framework. So if we want to write Jacobian in the matrix form, we have this equation. It is very important to mention one point. As you can see, the Jacobian matrix is equal to the stiffness matrix. This has happened in this case and for the isotropic material, and this is not necessarily always happen for any type of materials. Writing this relation and this matrix is your main job. It's true that there are relations for the default elastic mode in the Abaqus library material, but the process is important here. The main part of your job is to prepare these relations for your material and write them in subroutine. Of course, this section has nothing to do with subroutine writing and requires more computational theory of elasticity and plasticity. It doesn't matter if your model contains elastic properties or plastic or damage. You need to get these relations for all the properties and get the equations for it. Note that if you use subroutine for the material, you can't use any of the properties of the material, such as plastic or damage or anything else, in the software's user graphical interface. And Abaqus ignore if you enter any value in the property module in creating material dialog box. Well, it's time to move on to an example of isotropic elastic material. But before that, let's summarize what has been said. We said we need to define the relation between stress and strain. Next, we need to copy the UMAT interface to a code editor. Then write a code that identifies three things. 1. Calculate the amount of stress at each step and calculate for the next increment. 2. To calculate the stress, the Jacobian matrix must be written in the code. 3. Before that, we need to get the value of the components of this matrix from the theory of plasticity and elasticity and so on.